Welcome, everyone, to this captivating journey into the heart of quantum physics, where reality is more mysterious than we could ever imagine. Today we'll unlock the secrets of one of the most enigmatic concepts in this realm, Heisenberg's uncertainty principle. Our story begins in the early 20th century, a time of great scientific upheaval. Visionaries like Werner Heisenberg, Niels Bohr, and Erwin Schrödinger were rewriting the laws of physics, redefining our understanding of the universe on the tiniest scales.
Part of this groundbreaking revolution was the realization that when we explore the behavior of quantum particles, we enter a realm of uncertainty, where the very act of measurement becomes a profound challenge.
In this video, we will venture deep into the mysteries of Heisenberg's uncertainty principle, a concept that fundamentally altered our perception of particles and their properties. So fasten your seatbelts as we embark on a journey to explore the limits of our knowledge, where the more we try to measure, the less we seem to know. Historical background. To truly grasp Heisenberg's uncertainty principle, we must first step back in time to the early days of quantum mechanics. It was a time of scientific revolution, where classical physics was struggling to explain the behavior of particles at the atomic and subatomic level.
In the early 20th century, visionaries like Werner Heisenberg emerged as pioneers in this scientific upheaval. They questioned the classical notion that everything in the universe could be precisely measured, including the positions and velocities of particles.
One of these visionaries was Werner Heisenberg, a German physicist whose groundbreaking work would forever alter our understanding of the quantum world. In 1927, Heisenberg introduced what would become known as the uncertainty principle, a concept that shook the very foundations of physics. This principle challenged the idea that we could simultaneously measure both the position and momentum of a particle with infinite precision. It introduced a level of uncertainty that had never been encountered before.
But to truly appreciate the uncertainty principle, we need to dive into the mathematics behind it. In the next part of our journey, we'll explore the mathematical expressions that define the uncertainty in quantum measurements, and you'll begin to see why this principle is so profound.
Uncertainty in position and momentum. Welcome back to our exploration of Heisenberg's uncertainty principle. In this part of our journey, we'll dive into the heart of the principle, understanding the uncertainty in measuring both the position and momentum of quantum particles.
Imagine you want to precisely determine the position of an electron. Classical physics would suggest that with the right tools and precision, you could pinpoint its location with absolute certainty.
However, as we delve into the quantum realm, Heisenberg's principle tells us a different story. It tells us that the more precisely we attempt to measure a particle's position, delta x, the less precisely we can know its momentum, delta p. This is encapsulated in the mathematical expression delta x delta p h with stroke /2, where h with stroke, h bar, is the reduced Planck constant, a fundamental constant of nature. Simply put, it means that there are inherent limits to how precisely we can simultaneously measure both the position and momentum of a particle. The more certain we are about one, the more uncertain the other becomes.
This principle is a core tenet of quantum mechanics and challenges our classical intuitions about the certainty of measurements. To grasp its significance, let's explore how this uncertainty plays out in real-world scenarios, from particle accelerators to electron microscopes, in our next part.
Stay tuned as we unravel the mathematical intricacies of Heisenberg's uncertainty principle, the mathematics behind the principle. Welcome to the heart of Heisenberg's uncertainty principle, where mathematics reveals the profound nature of quantum uncertainty. The mathematical expression for the uncertainty principle, delta x delta ph with stroke 2, encapsulates a fundamental truth about the quantum world. But what does it really mean? Let's break it down. Delta x represents the uncertainty in the measurement of a particle's position, and delta p is the uncertainty in its momentum. The constant h with stroke, known as the reduced Planck constant, is an incredibly tiny number. This is a key factor in why quantum uncertainty is so pronounced on the microscopic scale.
When we multiply the uncertainty in position, delta x, by the uncertainty in momentum, delta p, the product is always greater than or equal to half of h with stroke.
This means that if we try to precisely determine the position of a quantum particle, the uncertainty in its momentum increases, and vice versa. It's a trade-off imposed by the quantum world. To put it simply, the more we know about one property of a particle, the less we can know about the other. This isn't due to limitations in our measurement devices, it's a fundamental property of quantum reality.
This mathematical relationship challenges our classical intuitions, but opens the door to the intriguing mysteries of the quantum universe.
In the next part of our journey, we'll explore the profound implications of Heisenberg's uncertainty principle, and how it reshapes our perception of reality. Implications of the uncertainty principle. As we venture deeper into our exploration of Heisenberg's uncertainty principle, we begin to encounter its profound implications for our understanding of the quantum world. Imagine you're in a laboratory, trying to measure the position of an electron with incredible precision. Classical physics would suggest that with enough sophistication, you could achieve this goal. However, Heisenberg's principle steps in as a fundamental limitation. It tells us that the more precisely we try to measure the electron's position, the more uncertain its momentum becomes.
This uncertainty extends to all particles on a quantum scale. It challenges our classical notion of a deterministic universe, where everything can be known with absolute certainty.
These implications are not just theoretical, they manifest in the real world. For example, in particle accelerators, scientists strive to study the tiniest particles by precisely measuring their positions. However, the uncertainty principle imposes a limit on how precisely we can determine these positions, introducing an element of unpredictability into particle interactions. Similarly, in electron microscopes, which provide stunning images of nanoscale structures, the principle reminds us that there's an inherent limit to how much detail we can capture. So while the uncertainty principle challenges our classical intuitions about certainty, it also guides us in understanding the boundaries of the quantum world. To grasp its full significance, we must delve even deeper into the quantum weirdness in the next part of our journey.